Welcome, this is Ad Emmen reporting live for Premier Magazine from the ISC conference in Frankfurt. And we're here with Norbert Eickhardt, who is from the DEEP-EST project, which is one of the Horizon 2020 projects which develops technology for supercomputing. So welcome.
Hello.
Can you tell a little bit about yourself?
So I'm working in Jülich Supercomputing Center. Leading their technology development in the field of supercomputer architectures. And so what we do in the DEEP-EST project is to think about how the cluster technology, which is kind of the common standard in HPC right now, how this can be developed into the future, and especially on how to organize heterogeneity in future HPC architecture.
Future architecture can be quite broad. Are you concentrating on one specific item in the architecture?
It's about supercomputing architecture, so it's not really about how to build processors or how to build fabrics, but how to bring everything together. And this became more and more complex during the last years due to the fact that the mainline general purpose CPU is not powerful enough or not energy efficient enough in order to really power the large-scale supercomputers. And so we have to think about how to get some accelerating devices included into that. And so this is what is really special about this DEEP series of projects, and this is how to integrate those heterogeneous components, compute components into a single system. And the standard approach there is that you build kind of accelerated clusters. So which is you have a standard cluster, put in accelerator devices in all the nodes, and then just scale out with these nodes which are heterogeneous in a homogeneous fashion. And we do it the other way around. So we start with homogeneous nodes, but having different types of them, and then scale out these different types independently. So we started with the DEEP project, and there we developed this so-called cluster booster concept, where we have a standard cluster with general purpose CPUs, and a second cluster built out of accelerators, or out of many core accelerators. And this is what we call the booster. Basically, it's just a cluster of accelerators, but you have to give it a name. Yes. And now in the DEEP-EST project, we do the next step, so to go not just to two components, but to go to multiple components. So what we especially include is data analytics, so a part of the system which is capable to do data analytics, which is similar to a cluster, but typically you need larger memories in the nodes. Maybe you need accelerators like FPGAs or GPUs in the nodes. And so this forms yet another module. And the main purpose of the project is not actually, finding out that there are different ways on how to configure the modules, but how to bring the modules together. So how to develop the software which is capable to run this kind of system, that is capable to manage the system, to develop programming models, programming paradigms in order to separate the different parts of the application that requires this different type of modules, and how to improve the application software to make use of these heterogeneous architectures without throwing away the whole code, but to just morph the code into an application code which is modular supercomputing architecture ready. So let's name it like that.
So the main contribution is basically the architecture, bringing things together in a modular way. Is it disruptive in the sense that nobody else can use it except you? Or is it, do you intend to just roll it out later on?
Oh, no. So first of all, we want to distribute it, and it's also, so the idea is kind of disruptive, but we try to make it as compatible to the, let's call it old paradigm as possible. right? So you cannot go to some scientists and tell them, oh well, so just throw away all your million lines of code and start from scratch again. But the idea is that so all the applications are basically MPI applications, and that you just have to annotate your MPI applications, and then there is a tool chain which is capable to take the specific paths which will run on, say, on a cluster side or on the booster side, and compile binaries which are then optimized to both sides and which are still coupled together via MPI. And in fact, so even the MPI standard or parts of the MPI standard, which are 15 or 20 years old, already have all the ideas included. They were not yet used, but they are there.
In the previous project, you developed prototypes or testing systems which are at your center, I believe? Or not?
Correct.
So are they also used by application people? Or?
Oh yeah, so one important part of the project is that the application peoples are involved in the project. So they play actually a central part. So they, by analysis of their applications, they define how the hardware prototypes shall look like, how all the system software shall look like, and so this is a key ingredient of the project. So to get this information, and then afterwards, after all the hardware and software is built, we use this application in order to evaluate if actually our original idea works out. And so we found out that it works out.
Yeah. So it's really co-design. It's really good.
Yeah. So co-design is really at a central part. Is a central part in the project.
And what type of applications are you employing?
So we have different fields, and actually this evolved over in the course of the project. So one quite prominent example is this space weather application, which is provided by partner KO Leuven, and so it tries to simulate how solar flares interact with the magnetosphere of the Earth. Which, in the nice part, is responsible for the aurora borealis effect. But of course, there's also a backside of it, and this is that if such a solar flare hits, say, a satellite, it might destroy the satellite. And so it's important to know how this, how the solar activity has effects on the magnetosphere of the Earth. So this is one example. Other examples are in the current project. So we have GROMACS in. So in order to find out is this architecture applicable to this molecular dynamics simulation. We have a group from Iceland working on machine learning and data analytics. In the project, and so 3 more fields.
Okay, well, this gives already an idea.
Yeah, right. So the basic idea is to have really applications from different fields which try to cover. So the portfolio, large centers like Jülich or BSC, also partner in the project, have from their users, and so we don't want to develop a platform which is just capable to serve one application field, but to have a really a general approach.
What's the size of the project?
So all the 3 projects together got a funding of 30 million euros from the EU, or from the European Commission. So I think that the current project, it's a bit more than 10 million euros as funding. So we have partners, the application partners. We have partners building system software. We have partners building hardware. So in total, we have 13 partners, I think, in the DEEP-EST project.
Yeah, so that's quite a lot.
Yeah.
How will the DEEP results or the follow-on fit into the Euro HPC plans?
We think that this might be a blueprint for the future efforts in order to set up European systems. In fact, the outcome of the DEEP and deeper project, so the cluster booster architecture, is already utilized in Jülich. So you might know of this Eureka system, which is our general purpose cluster. And this was last year accompanied by a booster system based on kernel processes. And so we have this cluster booster concept already in production in Jülich. And well, so it's an idea. Everybody who likes to copy the idea is welcome to copy it and talk to us in order to get hints and advices on how to do that.
Okay, great. Okay. Thank you very much for this interview.
You're welcome. Thank you.
Primeur, this was Emin reporting from Frankfurt.